So let's continue our overview of plate tectonics by looking at convergent margins, what happens when plates collide. So when you're focusing on this material, I would pay attention to what happens when oceanic-oceanic plates collide, what happens when oceanic and continental crust collides, what happens when continental-continental crust collides. These are different outcomes, but they have really important implications for what regulates the size of our oceans. Lastly, I would pay special attention to this formation process of new continental crust in subduction zones. This is really key to growing the continents over time. So let's start with this example of an oceanic-continental convergence. If you're looking for analogs in real life, one of the great examples is the Cascade Range in the Pacific Northwest. This is the Juan de Fuca plate coming up against the North American plate, or the Andes, the South American plate coming up against the Nazca plate. In both cases, you have an oceanic crust that's being on a collision course with continental crust. And because the oceanic crust is more dense, it is basically forced down into the mantle. So the continental crust isn't moving, the oceanic crust is sliding, keeps moving, and subducts down into the mantle. So what happens here? Well, this is destruction of oceanic crust, so that's really key for balancing the production of new crust in spreading centers. But also, this is an opportunity for partial melting of the oceanic crust. You can see this depicted here. Once you go down a few hundred kilometers below Earth's surface, the temperatures are high enough for part of the ocean crust to melt, and you form these water and volatile rich magmas. They tend to be rich in silicon as well. So this is a chemical separation that happens during subduction. And then these volatile and silicon-rich magmas come up, they burn their way through the ocean, the continental crust, and they add to it. So the magmas cool, they add to continental crust, and also this forms lines of volcanoes right at the edge of the continent. So this is an example of volcanoes throughout South and Central America. For instance, there's a trench in Central America following right here, and that corresponds to where volcanoes are observed today. Similarly, there's deep ocean Peru-Chile trench that sort of feeds the volcanoes throughout the Andes. This is one of them. This is Sabancaya volcano in Peru. You can see it erupting here. These tend to be very gas-rich eruptions. These are quite different actually from what's observed in places like Hawaii, which is not formed from subduction processes at all. But this here, these are volatiles that were once part of the descending ocean crust that are being mobilized due to the high temperatures and the melting that allows. They're coming back up to Earth's surface and releasing carbon dioxide. They're also pumping water back out into the atmosphere. So this is a way of recycling Earth's materials. You can see a much bigger eruption here, but a similar process, a similar big cloud of volcanic ash and smoke and gases in Mount St. Helens eruption in Washington. So the oceanic-continental collision is very similar to the oceanic-oceanic collision. In both cases, you form a subduction zone where one plate goes below and is destroyed back as it heads into the mantle. For this case of the oceanic and oceanic collision, the question is who wins, right? You have no fundamental differences in density between an oceanic plate and an oceanic plate. That said, the older the plate is, the more it's cooled from its formation, the more compact it's become, and the lower it sits in the mantle. So it tends to be the older plate in this oceanic-oceanic plate margin that is forced into the mantle and to subduct and degrade. You have the same process though when you are taking ocean crust and you're setting it on this journey down into the mantle. Some of it is going to turn into liquid, turn into magma, and that magma is going to come up and it's going to form volcanic island arcs, and that's going to build, essentially a new continental crust. This is rich in silicon, like the continental crust. It's also a way for volatile elements like water to come back to Earth's surface. So between the continental-oceanic boundary and the volcanoes along South America, and then the oceanic-oceanic boundaries along the West Pacific in places like the Marianas in Japan, and the Philippines, this is sort of completing this ring of fire throughout the Pacific. So usually plate tectonics is shown in these kind of cartoon schematics like we've been showing already, but what's really remarkable is you can see the evidence for this process is totally compelling. This is earthquake depths that are sort of mapped through a section in Japan and through South America. So this is the spot of the Japan Trench here. You can see there's shallow earthquakes until you reach the trench, and then the earthquake location deepens. And this is basically tracking the subducting oceanic crust as it slides beneath the oceanic crust and triggers these earthquakes that are basically at the release of energy from friction between the two pieces, between the plate and the mantle. You see the same thing in South America here. You have the Peru-Chile Trench, then you have this subducting crust here, and that as that's being subducted, it's releasing all this energy through earthquakes. So you can basically track the motion of plates through earthquakes. Now there's additional techniques that have been developed tracking from the energy released in earthquakes, the waves that propagate throughout Earth's surface. Based on how fast those travel, you can tell the density of the different parts of the mantle. And so what you're seeing here is this sort of seismic imaging here. So blue colors are going to denote fast wave travel, and that's due to more dense material here. So you can think about this as the cold, dense oceanic crust that's being subducted into the mantle. And this is what subduction actually looks like in real life. Each of these plots have these kind of arrow marks. These are sections throughout these oceanic-oceanic collision zones. And you can see, for instance, here in this Kuril Islands area, you can see that you have this blue color here that's subducting oceanic crust. It's more dense, it's blue, and you can see it descending into the mantle. You can see that in all of these tracks here. This is Japan. You can see that the Pacific plate is being basically forced down beneath Japan, and it's descending into the mantle. So I think this is remarkable. On the right hand, you can see the same thing happening in South America. You have the Nazca plate being basically thrust down into the mantle below South America, and you can see this throughout all these different tracks here. So this completes the ring of fire here. This subduction zone processes allow melting that create the fuel for volcanoes that rim the Pacific. So from Alaska down to South America, this is mostly through continent-oceanic collisions. On the other side, this is mostly through oceanic-continent collisions. The Pacific plate is being destroyed, and some of that material from that plate is coming back up through these volcanoes. Just to walk through the chemical transformations in a bit more detail here, this is a throwback to when we were looking at the formation of Earth. But we have oceanic crust that's basically the same composition as Earth's mantle. It's got magnesium, it's got silicon, it's got oxygen, it's got things like iron in it as well. And this overall forms rocks with a density of around 2.9 grams per cubic centimeter. Now, as that oceanic crust ages, it gets modified based on interactions with water that percolates through its pores, also through things like calcium carbonate. So calcium carbonate is a shell that's made by marine organisms. When those organisms die, it ends up on the seafloor. And this is a major way to take carbon and calcium carbonate and take it from Earth's surface and push it back into the mantle so it's out of the atmosphere. This is a sink for carbon that we'll talk about more in the carbon cycle. At the same time, we're losing heat in this process. So we have an altered oceanic crust. It's got water, it's got carbon, it's lost heat, and this is going to be sinking at the oceanic trench until it gets to a point where this chemical separation can happen and form new continental crust. So the part of the magma that's mobilized is rich in silicon, it's rich in oxygen, it's depleted in things like magnesium. Look at how small the magnesium content of the continental crust is compared to the oceanic crust. Similar for iron as well. So this is a chemically distinct magma that comes up. It comes up with these volatiles, with water, with carbon dioxide that escapes from the decomposition of calcium carbonate. These go and escape to the atmosphere in volcanoes. This solidifies and forms new continental crust. So now we have a mechanism to form both oceanic crust at mid-ocean ridges and a way to form continental crust in both island arcs when you have oceanic-oceanic collisions, and when you have in mountain ranges like the Andes when you have continental oceanic collisions. This is a way to form new continental crust from this modification of oceanic crust. Now what's interesting here is we're basically taking a lot of the light elements, and those are coming up to form less dense continental crust at 2.7 grams per cubic centimeter. This leftover slab can be quite dense. It's more dense than the upper mantle, and actually this is a main drive for how plate tectonics works. We're generating these slabs that are descending into the mantle. They're cold and they tend to be heavy, and so their density is around 3.8 grams per cubic centimeter. They want to sink through the mantle, and that's going to pull the rest of the plate along with it. So Once this modification takes place, you're generating a more dense slab, and that's going to be pulling the rest of the plate towards the subduction zone. And that's going to be, you can track that all the way back to the mid-ocean ridges, which is going to be pulling things apart, allowing more ocean crust to be generated as the plates diverge. So just because I couldn't resist, there's some footage of what these underwater volcanic eruptions look like at oceanic-oceanic convergences. These are processes that will eventually build an island arc. But you can see here there's this West Mata eruption site here. This is what it looks like in more detail. You can see there's this Tonga Trench right here. It sort of separates this higher standing oceanic plateau region. This is where a new island arc is being formed as the Pacific plate is being subducted underneath the Australian plate. So this is video from an underwater eruption that was observed at this volcano here. You can see, look at all the gases coming out. This is carbon, this is water, this is a bunch of other elements that are coming back out in volcanic gases. They're returning from the bottom of the Pacific plate back up through this volcanic arc system. Look at all this lava that's being generated. This is distinct from lava, for instance, on Hawaii. It's more enriched in silicon and these continental crust forming elements. This is pretty remarkable. This can be captured on tape. Yeah, so pretty cool. So this partial melting of descending oceanic crust in subduction zones, that's one way to generate new continental crust, especially in places like the Andes where that magma will come up and it'll form part of these big granite blocks that sit underneath the continent. Another way to form and expand continents is through this process of exotic terrain formation. So to imagine here you have an oceanic-continental convergence zone with a subduction zone here. You have volcanoes being formed right at the edge of the continent. But as this process is happening, let's say one of these island arcs or one of these plateaus is being moved along and and comes up against the subduction zone. What's going to happen? Well, this island arc is it's formed of light continental crust, so it's too light to subduct back into the mantle. It's going to hang out at the surface and it's going to fuse with the continent. There's probably going to be a bit of oceanic crust and seafloor that's going to get trapped here and sort of be the glue in this fusion here. So at that point, right, you can't subduct crust anymore because this new island arc, this exotic crust is basically blocking that. But eventually, as more seafloor spreading happens, the oceanic crust is pushed into this new combination of original continent and fused island arc, this exotic terrain. And then you have a new subduction zone forming here. So this is a process that island arcs can come together and sort of add to the continents. And this is what has happened to sort of form large areas of the West Coast, such as California, such as Alaska. So this dark color here, this is sort of the original extent of the North American continent. And all of these bands here are different island arcs that have come in through this exotic terrain process where they've headed towards the North American continent, approaching subduction zones, terminated those subduction zones, new ones have started, new island arcs have come along, and over millions of years you can see how this builds out all the major mountain ranges on the Pacific West Coast. Baja California is another great example of this. So what about when two continents are pushed towards each other? What happens when a continent and a continent collide? Actually, this process is kind of similar to what we just saw with the exotic terrain formation. It's just more extreme because instead of island arcs, these are full continents that are colliding. But in this same case, continental crust is too light to subduct back into the mantle. We only have, and so instead, these crusts basically combine, they stack on top of each other, and high mountains are created instead. This produces a region with large earthquakes, but no major volcanic activity because there's not a lot of melting going on here. There's no subduction into the mantle, so this isn't creating new melts that are rising up through the crust. So continent-continent collision is usually preceded by subduction of oceanic crust at oceanic-continent convergences. So this starts like the exotic terrain process, and then you have this oceanic crust that has been subducted, that eventually breaks off, and then you keep having these plates collide together. And eventually the edges of these plates are compressed, they're folded, they're uplifted into mountains. This is how the Himalayas were formed. This is how parts of the European Alps were formed. This creates crust that's twice as thick, that has really, really deep roots. And this is ultimately how ocean basins are closed, is that you have a constant oceanic margin that turns into this continent-continent collision because you basically run out of ocean. An animation of what happened when India continent collided with Asia a continent. You can see there's all this subduction of oceanic crust that preceded it, that closed an ocean basin, and now you have this collision, this folding, this creation of the Himalayan mountains. It's a really complex, highly energetic process. It triggers lots of earthquakes. It bends basically all these rocks at the borders here. If you've ever looked at Pakistan, Iran from space, you can see these folds here. It's pretty incredible. So it's really the fact that you can't subduct continental crust during collisions that generates the really tall Himalayas and the Tibetan Plateau that stands behind them. This is the roof of the world because it's being pushed up by ultra thick crust because it's basically combining two separate pockets of continental crust. The front range of the Himalayas actually is a bit of ocean floor that's got caught in the wrong place at the wrong time and thrust all the way up, the highest elevations here. And there's actually marine fossils that you can find pretty high up in the Himalayas, whether they're fish, whether they're shelled organisms. There's a record of this, the highest part of the world being at the ocean floor in the past. Now today the Himalayas are, they're still growing, but they're also rapidly eroding as well. And so this is a big process that we'll investigate when we talk about the carbon cycle. This is dumping a whole lot of sediment and river water that's enriched in different elements back into the ocean. So this is a key part in global elemental cycles, the creation of new mountains and then their erosion. So in this video, we looked at what happens when plates collide. There's different results, whether you have an oceanic-oceanic collision that creates island arcs, an oceanic-continental collision that creates long mountain ranges and adds to continents, or continental-continental plate boundaries that create these really high mountain regions because nothing subducts. And so ultimately, new continental crust can be formed in subduction zones because of partial melting. It takes the lighter elements, the volatiles from the altered oceanic crust that's being subducted into the mantle, and those materials are, as a magma, they're coming back up to Earth's surface, they're burning their way through crust, they're adding to the crust, they're making it thicker, and they're reintroducing things like carbon dioxide and water and other gases back into the atmosphere. So this is how plate tectonics helps establish a cycle of material flow from the atmosphere, the oceans, the crust, and all the way back up again.